So, Professor Pusari, all that fine? Pune?
Yeah, everything is fine, sir. Yeah. Yes.
They will discuss your seminar.
Yeah. I
So,
have
Puri Sahib, you are in
finalized
the
the
office?
contents.
No. I am
Huh?
at home. We are
Ah,
working
okay.
from home.
Your number of
Nobody.
medals are equally located in home also.
The office is closed for the last 3 weeks.
Ah, right. So, here is a moderator, Dr. Gopal Rai.
Yes, sir. Namaskar.
Think
Oh, quite a good number. We are already 84. Normally, many people join around 4:15 to 4:30.
आज मैं ही कंफ्यूज था कि आज कितने बजे लेक्चर है. मैं 6 o'clock सोच रहा था.
क्या कर रहे हैं गोपाल?
मैं खुद ही सोच रहा था 6 o'clock लेक्चर है.
Yeah, I
Right.
also thought it was a usual time of 5 o'clock. Then I saw it was 4. Then I immediately joined right now.
Yes.
Well, let me share you. You see, these days, between 4 and 5, lot of prayer meetings.
Oh,
also
yes,
are
you're
there.
right, sir.
In fact,
Absolutely.
I also have
That's really a pity in
prayer
India.
meeting at
Really.
5. So this is has become a
Right.
big
So,
issue.
Mr. Hoffman, where are you located? Which country?
No, I'm located in the south of China, in Guangzhou,
South of
Canton.
China. So, you are at 6:30 now, 6:30 p.m.
Absolutely.
That is why we fixed up 4 o'clock, you know.
Thanks to all of you to
No,
help
I'm
me
just
making it a
informing
little bit
others.
earlier.
We have to certainly take care of this aspect, no doubt. So meeting times are varying nowadays from 4 o'clock, means 4 p.m. to 6 or 7 p.m. also. We had once a speaker from US, it was 7 p.m. to start. So all kinds of variations. So now it's about 4:07. We can start maybe in another 2-3 minutes. At 4:10 we can start, Deepika.
Yes, sir.
And has Ruhi joined in or no?
Yes, she is with us.
Okay.
Yes, sir, I'm there.
Okay, Ruhi. So you're back from your holidays and whatever leaves, etc.
Yes, sir.
Good. Any idea about Mr. Devte, our DG?
no, sir. I mean, not communicated it.
Because last time he could not join in.
Yes.
And I'm not seeing him now also.
I think let's start. There are about 75 participants.
Yes, once we crossed 70, 80, it's okay. We can start.
Yeah, we can
are
start.
reaching close to 100 now.
Yeah, Deepika, we can
Okay,
start.
so Deepika and Swapnil, all yours.
Yes.
And Ruhi, of course.
Yes, sir.
Good evening, everyone. We welcome you all to the IIB lecture series. Today we have with us engineer Pierre Hoffman, who will be speaking on fiber reinforced polymers, rebars, used as permanent reinforcement in RC structures. So to begin this event formally, I would like now to hand over it to engineer Swapnil Joshi. Thank you.
Thank you, Deepika, and very good afternoon to everyone. I would like to officially welcome you all for today's lecture series number 21, wherein the presenter is Engineer Hoffman. So before going further, let me request Ruhi to play a introductory video of IIB. Ruhi, can you just please place the video?
Yes, sir.
before we formally get into the today's session, let me invite our President Sri Vinay Gupta ji to say a few words about the lecture series and overall initiative. Vinay sir,
Thank
over
you.
to you, please.
Thank you, Swapnil. Good afternoon or good evening to Mr. Hoffman. So, and good afternoon to the Indians the moment. It's really a privilege for us to have speakers who are of this stature, who are able to narrate all kinds of new materials, technologies, and various aspects of design and construction to us, which certainly without you people's knowledge, we would not have it. So my sincere thanks go to Mr. Pierre Hoffman for today's deliberations. Friends, let me tell you that IIB started in 1989. For some, of course, it's a repeat, but it's better to clarify once again. With a small strength by our then Director General, Founder Director General, Engineer MC Bhide, who retired from railways as chief engineers. And after the retirement, he decided to promote bridge engineering in the country, such an important aspect. Because very honestly, you know that in India, you hardly find any books on bridges. You hardly find any very set methodology for designing or constructing bridges, but you have been constructing a lot of them and you have been designing a lot of them. Talking of way back in 89, the bridge engineering technology itself was not so advanced. So a need was felt, and that is what Shri Bhide Saab did, that he started this forum for exchange of knowledge and ideas. Today we are 7,000 strong. We have a executive body, which of course you have seen. Dr. Gopal Rai is one of the two honorary secretary. Mr. Swapnil Joshi as another honorary secretary. And then we have a huge team of members of the executive committee. And all of us are self-propelled professionals involved in the design or construction or maintenance of bridges, including from highways, NHAI, railways, MORTH, consultants, suppliers, etc. As a part of our responsibilities towards the society, ever since the lockdown that started or COVID times started, we call it a new era. Of course, I hope it's very temporary. We started this special lecture series apart from other larger events. And today we are on 21st. So we have become adult now, 21-year-old. And we have this lecture by Mr. Pierre Hoffman. This topic of glass fiber polymer reinforcement, why it attracts us is we are always looking for durability, long-term, long-lastivity, sustainability. And therefore, for those aspects, it becomes very important to have some materials which have a long life. For example, we used to use, in fact, we use some, but not much, of metallic sheathing. But today we are replacing almost everywhere from metallic sheathing for pre-stressing to HDPE sheathing, that is high density polyethylene sheathing, which is more or less inert. It has any amount of life. There's nothing to worry about. We have already been using this glass fiber reinforcement, glass fiber polymer reinforcement in our metro structures. In underground metro that we are designing, in many of them, we do provide a soft eye. Soft eye, eye is always there, but soft eye in some. We also have hard eyes at times. In the soft eye, where you, in the station, where you enter with the TBM, rotating tuck, 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 and you enter the station. So soft eye is made out of glass fiber polymer reinforcement, which can be cut through very easily. But that is not the main purpose of glass fiber polymer reinforcement. There it is, of course, and if we design the structure for that reinforcement as glass fiber polymer, but, and of course, Mr. Lakshman Rao is very well aware of all this, I'm sure, Dr. Lakshman Rao. But idea is that we should try and use some materials which can give you a life which is, no life. It's like 100 years, 200 years, 500 years. So I'm sure a time will come that either you will have stainless steel reinforcement or you will have glass fiber polymer reinforcements. Of course, there are a lot of intricacies. There are design codes we have to worry about. In India, we don't have it. I think so. and the other intricacies about the creep and shear strength and all those things, which I'm sure, I mean, I'm very hopeful that Mr. Hoffman will discuss and enlighten us with all those things. So with these things, with these words, I will close my so-called short 5 minutes speech that I'm supposed to deliver. But I hope we all enrich our knowledge, including me, and we go back with happy memories of this lecture. Thank you so much.
Thank you, sir. Thank you
Thank
very
you very
much.
much.
Now let me introduce our today's moderator, Dr. Gopal Rai. Dr. Gopal Rai holds a PhD from IIT Bombay. His phenomenal level of prowess has enabled him to be associated with several prestigious projects, including Apsara Reactor, BARC, Mumbai Airport Bridge Strengthening of Mithi River, ESIS Hospital, etc. He is an honorary secretary of IIB, as Vinay sir has already introduced him. He is also a general secretary of Association of Structural Rehabilitation Retrofitting, committee member of ISSE, Mumbai Center, BIS and ACI. He has delivered more than 680 presentations nationwide and 27 presentations in international conference. He is also a keynote speaker and author in 4 international conferences and more than 10 national conferences. Dr. Gopal Rai has colossal research profile as well. More than 100 number of his research papers have been published in journals. Dr. Gopal Rai got the award of 50 Manufacturing Innovative Leaders at World Innovative Congress Award 2019. Also in Dubai for 40 Most Influential Leaders Under 40 Years 2017-18 by Asia One and many more. I welcome today's moderator Gopal Rai. Deepika, is he there because he was facing some network problem?
Yeah, Swapnil, I'm there.
Yeah, okay.
Yeah.
Over to you,
Thank you.
Gopal.
Yeah, thank you, Swapnil. Thank you, Vinay Gupta, sir. And thanks to all the IIB team. I think the subject which is there, the composites, which is very close to my research and all. And really, it will be wonderful to listen to the one of the renowned author. And before that, let me introduce to Swapnil. My voice is clear.
Yeah, voice is clear.
Yeah. Let me introduce today's panelists first. The first panelist today is Mr. Umesh Rashirke, sir. Let me introduce him first. Rui, can you play the slide? Yes. Shri Umesh Rashirke, sir, has over 30 years of experience in the planning and design of bridges, flyovers, large span steel structure, marine facility, industrial structure, plisters and and reinforcement concrete structure, shell structures. He graduated from VGTI Mumbai in 1987 and he does his master's from IIT Madras in 1991. He was involved in design of many prestigious structures like cable stay bridge on rivers, Mapusa and Bhopal, Patna, Baroda, etc. Number of precast segment bridge, metro rail, viaduct, long span steel truss, an arch bridge. He's member of various BIS and IRC committee and published number of papers in national and international conferences and journal. Thank you very much, Umesh Rashirke ji.
Yeah, thank you.
For becoming the panelist today. Let me introduce to the second panelist today with us is engineer L.R. Mantri, the South Region Design Head from AFCON Infrastructure Private Limited. Let me introduce him, a competent civil engineer with more than 17 years of experience in civil engineering project coordination, design coordination of underground metro projects, design, tendering, risk analysis, monitoring, execution of different projects work, slope stabilization works, geotechnical investigation work, including offshore, near scope of work, preparation of technical specification, evaluation of and many underground soil structure, structure such as cofferdam and sheet pipe work, deformation of tunneling lining work, protection and river training work, all more or less all type of underground structures he has come over. MSW landfill wall, then hazardous waste landfill, slope protection measures, and also in various like roads, railway, industrial, residential, commercial building, water supply, power plant, oil, gas, in all type of the industry which are there. He has already worked as a major consultant come the execution part. Welcome to LR Mantri Saab. Welcome.
Thank you.
Let me introduce to today's third panelist, Engineer Navneet Gupta, Assistant Vice President from Tandon Consultant Private Limited, New Delhi. Let me introduce him. Engineer Navneet Gupta has 25 years of extensive experience in structural engineering, specialized and expert in the field of underground MRTS, structured bridges, flyover, underpass, multi-level grade separators, long span river bridges, elevators, MRTS, viaduct, railway and dedicated freight corridor bridges, expressway, elevated highways. He did his master's in civil engineering from University of Roorkee, and now IIT is known as IIT Roorkee. After completing his BE in civil engineering from RC Nagpur. Welcome to Engineer Navneet Gupta ji. Namaskar, sir. Now,
Thank you, sir. Thank you, sir.
It's pleasure to introduce today's the speaker, the engineer Hoffman. Welcome you, sir. And
thank you very much.
Yeah. First of all, thanks for accepting. And let me introduce your the profile. Engineer Hoffman graduated with Master of Engineering from Ecolo Centro de Lille. Can you pronounce, sir? If you like, if I'm
yeah, very fine. École Centrale de Lille. Yeah, forget for the sorry for the French name.
No. Let me learn also from little bit French from my daughter also. So this is what part. And Masters of Science in Project Management from Sikima. Yeah.
Correct.
Okay. He joined Dextra in 2007 to develop fiber reinforced polymer soft eye technology used in metro systems. He led the development of FRP anchors used first on Doha Metro Qatar, then in India DMRC's phase 3 or phase 3, Bangalore Metro and Nagpur Metro. Likely he has been promoting FRP as a permanent reinforcement and substitution to steel rebars, which was adopted in 2018 on the world's largest underground oil storage. After 14 years at Dextra, Mr. Engineer Hoffman is General Manager for Geotechnical and Product Lining. Welcome, Professor. Welcome, Engineer Hoffman, for today's talk.
Much.
Yeah, and I think with this, without giving much time, let me like you can go ahead with your talk. You can start with your presentation. Vinay Gupta sir, can we start?
Yes, please go ahead.
Yeah, over to Professor, Engineer Hoffman. You'll start, sir.
Thank you. Perfect. Thank you. Thank you very much. Let me.
You will become professor soon. The way it's being pronounced again and again.
It's a easy way to become professor. Thanks so much. Thanks so much for promoting me. I have to admit that that's not what I am. I'm humbled again to be invited. I know some of you panelists, maybe also in the audience, had the chance to travel to India in the past to discuss or even to present the soft eye technology we mentioned. Typically with the ICI conference and this kind of events. But today, indeed, we wanted to have a new angle on this material, GFRP rebar. As Mr. Vinay Gupta explained, even though soft eye, we use them for 25 years, it's a bit of a shame, we find, to have such a beautiful engineered material and only use it to destroy it after 1 or 2 years. There's so much more we can do out of it. So today's presentation will be focused on permanent application. We will start with a quick introduction to review the material properties because we cannot assume that everyone is familiar with that. As I say, people involved in tunneling would know. But after that introduction, we will dive into specific aspect of permanent durability, lifetime, Mr. Gupta mentioned shear creep. Actually, I had the difficulty. I couldn't squeeze all this into 45 minutes. But if those topics are raised in the panel section, I would be more than happy to tackle that. So yeah, let me try to give you a first presentation in the short time, and happy to take much more question in the second part. So as I say, first introduction and properties. Let's look at a bit of definition. So FRP is a big family of material. FRP stands for fiber reinforced polymer. As the name stands, on one side, we are using a type of fiber. At Dextra, we use mainly two. Glass fiber, we have many different grades of glass fiber or carbon fiber. I would say in 90% of the cases, glass fiber is suitable for the application. We really only use carbon fiber for very specific high performance, heavy duty, or some very big concerns. We address it with carbon fiber. The glass is really the general purpose material that we can address most application. The fiber would probably give most of the mechanical performance, while the resin on the other side is really what will give the durability of the product. So typically we use polyester for the temporary application. So again, we mentioned soft tie, tunneling, we'll use polyester because it has a shorter lifetime. When we look at permanent application, we will have to upgrade to other type of resin, typically vinyl ester or epoxy. So looking from a supplier point of view, I mean, Dextra as a manufacturer, as a supplier of this solution, we really have to see that those elements, fiber and resin, they are our raw material the same way a steel mill will be able to play with the chemical composition, playing with the carbon content, playing with the other chemical elements, manganese, phosphor, to create a ductile steel, a high performance, very high strength steel, or to produce stainless steel. The same way, by selecting the right fiber, the right resin, and together with the right process, we can give very different properties to the FRP product. During this presentation, we will mostly talk about GFRP, G again standing for glass fiber reinforced polymer. So what are those FRP rebars? Because again, I'd love to talk to you about everything about FRP. We'll really focus on reinforced concrete applications, so RC structures. I would have loved to talk to you also about caverns for oil storage, oil and gas. This is also another topic we tackle. But here we will really look at rebars, so substitution to the conventional steel rebars. The product we propose is a rebar following this geometry. We have two main features. One is the surface is sand coated. This is just to increase the roughness of the surface. So it will increase bonding with concrete. And the second feature is this helical wrap. So we see the spiral going along the bar. This will create surface deformation and create small ribs. The two features together will bring a great bonding property to GFRP. So as per the code, we guarantee 9.6 MPa, making this much better than steel rebar, of course, than steel strand, or even fully threaded steel bar. All those products will have a lower bonding property than a GFRP bar. This is one of the advantage we find with a GFRP rebar. And again, the objective is building on the strengths. Everything we will see in this presentation is to understand the properties of GFRP, its strengths, its weaknesses as well, and understand in which case it makes sense to consider GFRP as a substitution, but also in which case it doesn't make sense. Because I would say, I don't think any FRP manufacturer has the intention to replace steel in each and every application. It remains today a niche product that can advantageously replace steel in some application, and that's what we want to target. Let's look at the surface of the bar. So here I'm offering a picture that is a microscopic picture of the surface of the bar. Let's look at the left side first. What we see here is the edge of the bar. So basically what those big white spots you see at the bottom, they are actually sand, the sand grain. And you can appreciate the size compared to the glass fiber, individual fiber that are shown at the top left corner. You can see how tiny they are. They're only 15 to 20 micron in diameter. And this vast brown area here is actually resin. So we can see that the resin is really acting as a binder between the fibers here on the outside and the glass on the surface. But now, looking at the resin, those fiber area here, we can zoom in further. And what we find is the resin is also actually binding all those fiber together. So each individual fiber is encased in resin matrix. And so that resin will help to create additional protection again. So you have an outer layer, but you also have the resin within each asperity, each gap between the fiber, but also that resin will transfer the load. It's important to see, we are talking about composite material, so it's not monolithic. And it's important to have this resin acting well to transfer the load from the outside of the bar, its perimeter, and transfer the load towards the inside. The challenge with a composite material is to ensure that once the bar is under stress, the inner fiber can be stressed as much as the outside. It's never possible to reach that. So we have some limitation, but we try to transfer the load towards the core, towards the inner part of the bar as much as possible. And resin has this role to play as well. All right, so now that we understand how the product is made, again, I had to shortcut a bit of the process, manufacturing process, but it would be too long to review that. Let's look at properties and design. This is really what we should care for now. So first thing I need to explain is typical characterization of material would be to obtain a stress strain curve. So that requires to conduct a tensile test. Tensile tests are governed by a different standard. Most common is ASTM, D7205. However, the issue with GFRP material is it doesn't have linear behavior like you would get with steel. Steel, you can take a small piece, a big piece, cut a coupon out of it, send it to the lab, and then you characterize the grade of material. With GFRP, there's a size effect, we call it shear lag, and the big diameters don't have the same property as the small diameter, even though it's the same formulation. So we have to test the product in full section. So we don't test a coupon of the material, we test the product, the actual product. So we send to the lab on this drawing, it shows to a diameter 25. To characterize the diameter 25, we test diameter 25. We test up to diameter 51 for soft tie application. So huge bar, you need really big tensile machine. However, if you were to put the GFRP bar directly into the tensile machine, you would crush the bar. So we had to have to add those steel sleeves and fill them with grout so that the material is not crushed. And I think the interesting part is the outcome, the result. Once you finish the test, you can see the failure mode. We call this a brooming failure. This is typical behavior of a brittle material. A sudden failure and considering like glass. So these are all the characteristics of FRP material. On the stress curve, turns between GFRP the steel on the other side. So a typical steel rebar would behave according to the blue line that you see on the screen. We can clearly see the elastic phase, the yield point, the large ductility. On the other side, the GFRP rebar would behave differently in the sense it's a pure straight line, or consider a pure straight line. We can see the modulus of elasticity is much lower, so it's only a quad grade, I would say, or a middle grade, while steel is 200. However, again, once we exceed the typical yield point of a steel rebar, you see GFRP would continue to increase the load in the same proportional manner, and we will reach the ultimate without the same quantity of deformation. Since we don't have yield point, we don't have this ductility, and therefore much less deformation. I think for all the engineers that we are, once you see this graphic, it's very easy to understand that it is not possible to design a concrete structure reinforced by steel and a concrete structure reinforced by GFRP using the same design code. My point is, even if we were to just use the input the GFRP parameter into any steel design code, it would not work, because fundamentally the way the material behave is not the same. I would say if we try to simplify, while in steel we have a lot of safety, a lot of buffer. I mean, where the safety is in the design is that from the yield to the ultimate lot of deformation. With GFRP, since we seem to work low and take the time, actually GFRP and with steel, we generally work in the same area. I would say in the same, towards the same stress level. However, the same why we have to use different design code. I will talk today about the ACI standard, or ACI guideline, sorry, which is ACI 440. Mr. Vinay Gupta also mentioned rightfully that there's no Indian code for GFRP today. However, I'm familiar with the working group working on the IS. There were very interesting articles published on this in the ICI journal of last month, I believe. And it's very clear that ACI remains the worldwide reference. Looking at it today, much of the work of IS is let's say, is largely influenced by the ACI. To date, it looks like there's a large overlap. The good news is also IS seems to include some of the upcoming improvement and revision that ACI is bringing. But again, since it's not released today, this is our experience for India, and this is our experience all over the world. Since there's no truly international standard, most projects, I can say 95% of the project we work on, they are using ACI 440 to design. ACI 440 is among the ACI range, the one specific for FRP. So you can design ACI 318, you design steel rebar. ACI 440, you can design GFRP. And there's a full set of subsection. 440.1 is the design. 0.3 is the test method, so characterize the material. 0.5 is the construction, so for the contractor, how to install. 0.6 is specification for material, so it's a full set. And again, so looking at how the design methodology or the design philosophy of ACI, it's all about balancing the failure mode. I would say in a typical GFRP reinforcement project, we are trying to get both the rebar tensile rupture failure happening at the same time as the concrete crushing. And it's important again to remember, since GFRP will deform 4 times more than steel, it's definitely possible to reach concrete crushing relatively fast or relatively easily early in the design. So we really need to check carefully what is governing the design. And of course, in the design, the objective is to balance as much as possible to get something optimized. Again, I mentioned Dextra as a supplier of the material. I think it's very important to understand all those design methods, they are specific. In most cases, engineers locally might not be necessarily familiar or expert at using ACI 440, which is different. And so this is why it's important for the partner that you have to be able to offer a design that is optimized, a design that is correct and genuine. This is sometimes what we experience and find it difficult is it's easy to make shortcuts with those guidelines. Again, this is not actually a code, it's a guideline. And we can definitely see some safety concern if some people take shortcuts with GFRP. As you understood, we don't have this ductility, and so it's really important to pay attention to how the design is governed. So on Dextra side, I think we supplied 400 soft tie worldwide. I can say in the vast majority of them, Dextra was either the designer or assisting the designer in offering that. Likewise, when we do a permanent structure, we also work very closely with the owner, with the contractor, to come up with a good design. So let's look now at the product range. What are the elements available for us to design? Well, this is a vast table, but maybe just to remember in short, let's say a typical data sheet. At Dextra, we promote mostly two grades for permanent application. One grade that we call 45P, so it's a modulus of elasticity of 45 and P for permanence. We have another grade 50P, so 50 for, again, from the modulus of elasticity and P for permanence. But actually we go up to 60. This is less common, but we can offer 60 GPa. As you can see in our range for permanent application, we go from diameter 6 to 41 mm. And if you have a quick look at the ultimate tensile strength, this is connected to what I mentioned earlier. The smallest diameter will have the highest strength in MPa, while the biggest one will have the lowest. So again, here two examples of two different grades, but that's typical what you would expect. I mentioned about the V resin that is very important for permanent application. So V stands for vinyl ester. And also we offer bend bar, so stirrups from the diameter 10 to 25. Important aspect again about the bends is that all the bars being made by GFRP material and most particularly what we call thermoset resin, the material, once it's cured outside of the production line, it can't be deformed. In the sense, it can't be shaped, it can't be bent like you would do with a steel rebar. So that means Dextra involvement in terms of manufacturing. We are like the steel mill, as I say. We prepare the formulation, but we also need to do all the cut and bend work. Outside of our factory will come the bars already cut to length, already in the proper shape. So that goes from what we call conventional shape, C shape, L shape, or loops for piles typically. Of course, we can do also some more complex shape. However, they require mold tools to produce that. And so it's also important to work closely again with the designer to ensure that whatever the shape, the design that is selected from a manufacturing point of view, it will be possible to execute. And that's also why we work really closely with designers for that purpose. So at this stage, I think I've introduced quite in details the GFRP material. I would like to look specifically at now long-term performance and durability. So those are aspects that are traditionally not tackled or just little bit tackled with temporary application because we only care about 1 or 2 years. Here we will really look at what's happening on GFRP material over a long period of time. I would say there are really two factors that we are caring for when it looks at long-term performance. On one side, there is the mechanical impact, if I may say, so typically creep, again, was mentioned by Mr. Vinay Gupta earlier. But also on the other side, there will be everything related to durability, the environment, the degradation, the corrosion. So we will look at those two aspects, and this will give us two factors that we need to apply to the material. First topic, creep. Again, I think it's a nickname, but I think it's a very good way to summarize it, the static fatigue. So while fatigue will have some impact on the material cycle after cycle after cycle. Here, creep will see the impact on the performance. So typically we are looking at retention, creep retention, and it's related to a static load. As you would expect when you do a RC structure, here we assume our reinforcement is under a constant stable load, and we want to see the effect. We characterize it, the picture you see is a test performed by Dextra with a third-party partner. There's again an ASTM and ACI standard. We perform long-term stress of those bars at different percentage of the UTS. So again, if you stress it at 100% of its UTS, its ultimate tensile strength, you would get immediate failure. However, if you stress it, as we can see on this graphic, at a lower percentage, the failure will occur later. And please mind the scale here. It's a logarithmic scale. And again, here what we care for is, with a permanent structure, is probably the 10 to the power of 6, the million hours being 114 years. It's interesting to see that there's a regression, and it's behaving logarithmically. What we concluded on our material is, if the sustained load is maintained to a maximum level of 55%, we can guarantee the GFRP material will be able to take that load over 120 years. That's extremely important, because as a designer, once you start designing a structure, you should be able to limit the sustained load to this value. And that's also considered in the codes, but we wanted to have it replicated. This is interesting because all those studies, we share them with the ACI committee and all those committee, and they use those data to update the standard. And we see that there's a trend now to update all those coefficients based on the value tested from the supplier. So to have something that is more realistic, as the material is improving over the last 20, 30 years, GFRP material improved a lot. And so the factors can be revised accordingly. The second aspect, as I mentioned, would be now environmental factor. So we are not looking at any kind of mechanical degradation. Now it's looking at chemical degradation. The main thing that could affect the performance of a GFRP bar is the alkali environment, so the high pH. And this is typically what you find in moist concrete. We know alkalinity is used in concrete. It's actually useful. It creates passivation and kind of protects the steel rebar. In the case of a GFRP rebar, alkalinity could or would degrade the GFRP bar performance over time. You can see here a tank that was installed. This was used to do comparative study between GFRP bars from Dextra here at the bottom of the screen, and some competition material at the top to have a comparison used for some projects. The purpose of this test is clear. Again, accelerated aging, understand what will happen if GFRP bar is in this environment over a long period of time. So how to do this accelerated aging? We just push the pH to a very high level, between 12.6 and 13. And also we make the temperature also very high, between 60 degrees Celsius. That means over a 6 months test, we can replicate again the ultimate time of 100 years or 120 years. And so the bars have been selected and taken after 1 month, 2 months, 3 months, 6 months, and we can see the impact over time. So typically, this is the kind of behavior we would see. So this is test we have conducted even recently. While GFRP will lose some performance quickly after, let's say, 1,000 hours, 40 days, we quickly plateau, and as we can see, it would generally retain about 80% of its strength over a long period of time. So while most standard require at least 80% after 3 months, what we've tested at Dextra, we were able to maintain this 80% plus even after 5,000 hours. That's almost 7 months. So that's really the interesting aspect is we know that steel material would corrode, would degrade, and that would even accelerate, that the concrete might burst and the concrete spalling, etc. The beauty with GFRP is really after initial loss, the reaction is logarithmic and almost zero. I mean, the further loss. For reference, this is not in the code or in any standard, but we ran the same test on by dipping the bar into saline solution. Very useful to simulate marine application. And you can see in that case, the GFRP bar from Dextra sample B was pretty similar to the competition here, 80, 85. So I would say the chloride and the saline water solution, typical effect on the bar would be similar to alkali or even slightly less. So this is not a concern. Using GFRP also for saline application, coastal area, this is particularly applicable. All right. Just before diving into application, which I think would be the biggest interest, let me talk about a key aspect, because lately I received a lot of questions about that, is environmental impact. So the impact of the GFRP as a material on, I would say the environment. So again, how does it compare to steel in particular? First thing important to know is the composite material. I mentioned resin, people are afraid, chemistry. It's important to know that once the resin is cured, I told you we can't change the shape, but also it's an inert material because all those molecules are what we call saturated. So there's no risk, even if you were to put that bar into, let's say, in contact with drinking water, or there's no concern for the environment at all. It's absolutely inert and there's no impact or nothing bad about this. What's very interesting is both the production and the usage of the product. So the second item, here you can see, I put the reference of the studies, but so for your reference, if you're interested, we can see that GFRP bar during production will produce 43% less CO2 emission than the steel bar, and also will require 46% less energy. I think in today's world, we see the population increasing. We know the concern about the environment and for future generation. This is already bringing part of the solution. I would say a big part of this is probably due to the fact that GFRP being 4 times lighter than steel, you are able to, that's one of the reasons why it requires much less for production. But something very interesting as well is on studies of the whole life cycle of the product, we can see that the impact on the environment with GFRP is 35% less than steel bars. The last aspect, I will illustrate it on the next slide, is purely about transportation. And I think this is one of the most powerful aspects. Allow me to summarize in this way. Since GFRP is stronger than steel, if we look at a simple application, a slab on grade with mostly temperature and shrinkage concern, we would be able to substitute a steel bar of diameter 12, 13, 14, let's say around this diameter, by a smaller size, typically a diameter 10 in GFRP. When the steel bar, diameter 13, I'm talking here, let's say on the US market, number 4, is about 1 kilogram per meter, the equivalent GFRP bar, the substitution bar, will only be 6.5 times less, will only be 160 gram per meter. And this is the beauty. Here I try to mention it in terms of truck rotation or delivery, but the beauty is also at site when it comes to steel placement installation. Everything will be able to go much faster, easier, because so much less material is required. All right. So I believe after reviewing all these aspects, we can really tackle now application. So what I would like to propose in the next 15 minutes is I will give you an overview of application where GFRP can be used. And I will also propose you a specific case study where we can see a substitution that has been done on a project. So originally designed with steel and how the calculation was done to say GFRP would be beneficial in replacing in that application. So you will see the application we will review. In many cases, corrosion is a big concern. That would be a main driver. Some of the niche application will look at some additional features, typically no magnetic interference, no electrical currents, or maybe thermal conductivity. I would say overall, in projects where specialized steel is considered, what I mean by specialized steel is epoxy coated, galvanized stainless steel. This is definitely a sign that it would make a lot of sense to consider GFRP rebar for this project. I'm not saying it will work every time, but it's a good sign that GFRP should be at least considered. And I would say in all applications, the weight reduction is an advantage. Generally come on top. It's not common to consider it itself. I'll show application. So first application, I think I had to start with that, considering the audience and the bridge engineers. For permanent application using GFRP is bridge deck. And there are 20, 30 years experience in North America. I think it's specific to cold areas because they have de-icing salts. So as you can imagine, in the northern state of US and in Canada, all the winter long, once the snow, the ice melts, it will infiltrate in the deck and will corrode. Some of the picture you can see here, this is the first generation, and I purposely took this to show you. The initial design was to use epoxy coated steel and just add a top layer with GFRP. But for the last 10 years, all the projects in Canada, all the projects again in the northern part of Europe, there's no steel rebar at all in the bridge deck. It's 100% GFRP reinforced. And that really shows also that we come to maturity. I mean, when people were reluctant using GFRP for, let's say, permanent and structural application, we are there today. People now, we have experience, we have background, we have case studies. They've done coring into those projects to prove that GFRP can really replace the steel rebar in the whole deck. Looking at other application, this is what I would call more of the niche, but it's true GFRP are used typically in MRI inspection room in hospital because there's no electromagnetic cage or field generated from that. But typically in many countries now they create toll gates that you can drive through without stopping using RFID technology. And so in those places, they use GFRP rebar for the same reason, or close to control towers in the airport. Marine application is something we definitely address more and more. I show you some of the early example of application we addressed. But again, I think it's very relevant for bridges. I'm familiar with some of the big projects you have in India, and I think many of them are related to coastal area. So you have a lot of bridges that would actually have piers in the sea. Think about intertidal area, think about splash zone. There are many aspects from the marine environment, and this is really an area where GFRP would make a lot of sense. So let me again show you, it's another very typical example of early design. This is a project Dextra supplied in Australia, Elizabeth Kay in Perth. And you can see that the designer at that time were not confident or not knowledgeable, I mean, there were not enough background knowledge on GFRP. So we can clearly see the D-wall being built with steel in the core area. With this part would be soil side, while the GFRP bar would be put on the outside in contact with the sea. And clearly here, the objective was to create an outer skin that would protect from corrosion. Again, this is a relatively old design. Today, we're able to offer the full cage in GFRP, and this is being done. Dextra now is working on 2 precast projects for marine application, one in Hong Kong, one in Australia, and everything has been designed with GFRP. Here we have example of a marine application but for repair. This is actually Pearl Harbor Dry Dock on the US Marine Base in Hawaii. And you can see how they use our GFRP to, they dowel the GFRP bar, the epoxy glue them. And then they're able to lay a new layer of concrete, and you're able to repair. Or this is a project we are now also working on in Thailand. So actually 3 hours ago, before giving this presentation with you all, I was presenting also this topic to Thailand, and they are using this for a jetty. So this you can see how we use both post-tensioning, we're using a steel member plus GFRP shear dowel. And we have a lot of questions also about shear, because every time the boat will hit the pontoon here, the jetty, there will be shear load applied to those dowels, and so we explain how we can do the design with that. Insulation, maybe just to mention very briefly, when you have a typical sandwich panel, precast sandwich panel, you can see the shape. The GFRP bar is used this zigzag to connect the panel together without creating a thermal bridge. So that's how it's working. Precast I mentioned earlier, but there are many precast applications as well that's using GFRP. In addition to everything we mentioned earlier, here the weight reduction is very critical for precast. So we are not so much looking at the reinforcement weight reduction. It exists, okay, GFRP is 4 times lighter, but the great saving is on the concrete cover. GFRP not being afraid of the corrosion, we can reduce the cover from 75, 50 to sometime going only with 30 mm, and that really reduce the weight of the concrete element, and that's a key factor for precast companies who are largely impacted by the transportation cost. I would say last but not least, those are maybe the application that we see the most now, slab on grade. I show you here a typical example of, let's say, rather homeowners application, driveway, parking lots, but we do a lot of industrial slab. So instead of using steel bars, going with GFRP, again, you see the spacing, can space them out, and really it's very easy and fast to install those projects. The case study I would like to talk to you today with the few minutes left is a project we've done in the Middle East, in Saudi Arabia in particular, where they are used to go on coastal area with epoxy coated steel, and they consider to replace it with GFRP rebar. I'm going to show you an industrial application, so this project here, but actually to let you know, they are going very far now in replacing slab on grade. I mean, in slab on grade is even in office building, like I'm showing you now, you can see that slab on grade are going with GFRP now. And this is purely for cost saving purpose. So let me enter in the last part of the presentation. I hope I still have a few more minutes, probably another 5 minutes if to follow the time frame. I will talk to you about what we call this Jizan flood channel case study. It is a case study for Dextra, but I can really say it is a worldwide case study. It has been published in several magazines in North America or worldwide because of the magnitude of the project. Let me maybe start with this picture, it's more obvious. We are dealing here with a huge petrochemical complex, a refinery built by the sea. And the main concern is to avoid a major flood in case of wave coming from the sea. So everything you see in blue on the screen is the flood channel. So if the wave arrives, then it will be detoured. I mean, it will not flood the industrial complex and would be channeled away. This flood channel I just show you, the blue line, is a 21-kilometer project. It's required 12 million meters of GFRP bars, and you will see we used diameter 13 for the project. Most of the bars are straight bars, but you can see there's almost 20% of the bars also required in bend shape. Looking at the geometry, the typical cut section of the project, I think one thing that is really massive also to understand is here at the bottom of the channel, the dimension were 4 to 74 meter wide. That's massive. Huh? And the typical bar used were straight bars, typically for the slope here. You have bend bar in those sections. And of course, it might not be very obvious, but you have plenty of dots here. All the longitudinal bars are straight bar, all the way going for 21 kilometer. So while we have the cut view here, you also have longitudinal bar installed on the project. So I show you those pictures. This is what the project install looks like. But let me show you the way the substitution was considered. And the consultant on the project really went through all the process. I believe it's ACOM who did this study. So what I'm showing is how the substitution has been done going from GFRP, from epoxy coated, to GFRP. So on this table, you will see the original design epoxy coated will be on the left, and the GFRP alternative is on the right. You can see that epoxy coated was considered with a tensile strength of 422 MPa, modulus of 200. So the GFRP material here was needed at 50 GPa, and they consider 600 MPa. So in that case, the 600 PA, you see the comment, is already factored with the environmental reduction factor of 0.7. So that's, as per ACI code, 0.7 is today the factor applied to consider the alkali resistance, the accelerated aging. And of course, in the design, we will also be sure that we don't go beyond 55%, the creep factor. That's also governed in the ACI design. So let's look at all the savings done on the project. One of the savings was related to the concrete mix. First, the water cement ratio was changed from 0.4 to 0.45, but also silica fumes and some other additive were removed because they are not required for GFRP. So that was one of the savings. I would say the biggest saving on the project was definitely that since GFRP bar had a higher capacity, but also since the crack width requirement could be relaxed from 0.3 to 0.7. Why? Because there's no issue having a larger crack. There's no risk for the corrosion of the GFRP bar, and therefore there's no risk for concrete bursting, concrete spalling. This allowed to increase the spacing from 150 to 200. This is great because every time, instead of putting 4 bars in steel, now we only put 3 bars in GFRP. One thing the designer didn't do on this project, and I think this was again this is again another example that it could have been improved further, is the concrete cover was kept at 75. For GFRP is really conservative. Especially, I would say, for the top part, it could definitely be reduced to 50 very easily. You can see also that lap length was reduced from about 1 meter in steel to 750 mm, and that's thanks to better bond strength. I'll be brief again because for time reason, but basically the overall looking at the reinforcement need, while 11 tons of steel reinforcement was needed, consider only 2,000 tons of GFRP material were required. You can see here the ratio is 5.5 times. I mentioned 6.5 in other example. That's typically what we expect on the substitution project for slab on grade. And the beauty here is the substitution from this epoxy coated steel to GFRP was cost neutral. that means any other saving on the project as a consequence of this change would be in the pocket of the contractor and in the pocket of the owner. So typically, contractor would save on steel fixing, while fixing GFRP cost on average double of the steel. Since you put 5.5 times less reinforcement, there were a big saving there, also on wastage. There's also saving on the concrete mix, as I mentioned earlier. And I think, again, one of the big saving that was not implemented here is the quantity of concrete could have been even reduced further from the concrete cover, but again, not on this project. The biggest beneficiary, if I may say, of switching to GFRP is definitely the owner. And that's something very obvious, I would say, on this graphic. This is information from the owner. If they design marine structure with epoxy coated steel, they only design it for 35 years. While with GFRP, they design it for 75 years. So you need at least to rebuild once the structure if they go with epoxy coated compared to going now with GFRP. And this being said, and yet, even though they designed for 35 years, experience shows that they would have to start maintenance after 8 years. While with GFRP, they won't have to do this. Again, because there's no degrading or self-aggraving situation of concrete spalling once the reinforcement is damaged, if I may say, with GFRP rebar. And that's really the big advantage. So I would say, all in all, to conclude, I just try to summarize with this slide. On the left side, you see the saving for the contractor. On this project, the contractor had directly in his pocket 5% saving by switching to GFRP, just on the supply and apply section. Of course, the biggest saving overall, the overall saving was 28%, and clearly the big saving was governed and pushed by the owner because it creates huge advantage in terms of maintenance for this project. So that means also for anyone who is pushing this technology, it means there's also a possibility to sell actually the GFRP alternative even at a premium, because for the owner, there's a big saving to do. So, okay, on this project, this is how it happened. But I think it really shows that both, let's say, the contractor and the owner, they really have a lot to earn from switching to GFRP, at least in those applications. And that's all for me.
Thank you. Can you close it? So, Dr.
Yes, sir.
Gopal,
Hello, yes, sir.
over to you.
I think, yeah, I think this is one of the, something apart from steel, now listening to the glass fiber, and we have gone a number of questions. I think Professor Surya Prakash is one of the expert in glass fiber rod from IIT Hyderabad is also there. But before I go to to all the external panelists, let me ask one by one to the first to Engineer Umesh sir to give his. Before that, there is a Dextra is a sponsors for this event. For this today's lecture was sponsored by Dextra. Okay. So I request Deepika, can you play one video? There's a video of Dextra, and we need to play the video. Can you play that?
Yes, sir.
And let me thanks to on behalf of IIT to Dextra for sponsoring. Thank you, Deepika. Let me short introduce also. There are close to 10,000 projects where Dextra is involved worldwide, and they are from for the three major industrial sites located in Bangkok, Thailand, then China and Mumbai. Dextra completely own a manufacturing facility and processes. This allow us to have a complete control over timing of our operations and quality of solution produced. There are following major projects in the segment like concrete reinforcement, rebar splicing, precast connection, and then composite FRP. I think let me thanks to Dextra for supporting this today's event, and in the past also they have supported. Thank you very much. And let me give you in one word, they are an innovative engineering company who adds the lot of like gaps between the construction and the innovation, and they come up with the tools so that we can smoothly work for a site. Thank you, Dextra, for your support for IIB, Indian Institute of Bridge Engineers. Let me go to now today's the first panelist, engineer Umesh ji.
Yes, thank you, Gopal.
Yes,
and
sir.
good evening, everybody. Dextra, actually, we are working with Dextra for my personally for last about 25 years back when we first time used this crimping of the bars at Kaiga Atomic Power Station. So since then, we are working with Sunil Desai, and had a really good experience working with the Dextra. Regarding this today's workshop or seminar, I congratulate Mr. Hoffman for giving such an informative lecture on this new product, that is glass reinforced polymer reinforcement. Though it has been used in India for this soft eye tunneling, especially in the metros, but we so far never used for a permanent structures. So with this particular introduction, definitely we'll try to use these bars for the permanent structure, and it has got a really good benefits, like what you told, that carbon dioxide reduction is about a 43%, and the energy reduction is a 41%. Overall, the impact on the environment with respect to the steel, it is a 41%, which is a really wonderful product. So good, congratulations for introduction of this such products in the industry. And with that, we have few comments like, see, we are saying that for the design, you are generally using the ACI, that is a 440. But here in India, for the bridge construction, we use a IRC 112, which is a more or less based on a European codes. Okay, so the philosophy of a limit state method and a lot of reliability based designs were derived from the Euro code. And fortunately, even in a FIB model code 2010, or say the new which is going to come, that is the 2020, the rules are given for design as a FRP reinforcement, as a non-metallic reinforcement in these codes. And there is one excellent document by FIB, that is a bulletin number 40, which gives in very great depth how to design a structure using this FRP reinforcement. So as somebody told, that we are developing our own national code for this FRP reinforced concrete structure. I think it should be based on the European philosophy, since our most of the national codes as well as the bridge codes are based on the European philosophy. Because ACI, the concepts and the methods are completely different. So there will be a lot of then confusion in the mind of the designers. So that was the first comment. Second, of course, it is quite a cost-effective solution once you consider this life cycle cost. Then there are some, of course, there are many question marks are there, whether this bar can be used in the compressive as a compressive reinforcement. Then what is its shear strength? What is its fatigue behavior? Then since there is no ductility, how to use it in a seismic prone areas? Then what are the, of course, factor of partial factor of safety, etc. The code will give the guidelines. Then another question is the coefficient of thermal expansion. I think they will be substantially different than the steel. And since the coefficient of thermal expansion is almost same for steel and concrete, we generally don't bother about that particular interface between the steel and concrete. But here, since the coefficient of expansion may be substantially different, so what will be its effect on the cracking, the micro cracking around the bars, and so those points you must have already answered or covered. And another on the same line, because of the low young modulus, there will be a good amount of a cracking as compared to the steel. And the appearance of the crack, though they are may not be, of course, they are not detrimental for the corrosion, as the corrosion is not involved in this bar. But from the aesthetic points of view, that we have to see what should be the limiting crack width for this type of a reinforcement. So these are the few comments. Of course, this effect of a temperature may not be that relevant since the bars are embedded in the concrete, and with a sufficient cover, there will be a good fire rating is available because of the cover of the concrete. But there will be, of course, number of similar questions. So once we start using it, those questions will get answered slowly. That's what I believe. So these are the few remarks or comments from my side. Gopal.
Thank you, sir. Thank you, Rajsarkar sir. Let me go to the second panelist, Mantriji, Engineer Mantriji.
Yeah. Good evening, all. We are so far in India. Dextra means the GFRP bars means we generally use it for the temporary applications, whether it will be a rock bolts in the tunnel section or in the eye seal. But today presentation is it's very enlightened that this GFRP can be used in permanent applications also. And in fact, we are using many Dextra projects in our various projects. So I will take this opportunity to thank you, Dextra, because for at any point of time, they are easy approachable for any kind of problem. And we used to get the solutions as per our requirements. So for this GFRP in the permanent applications, I have only one minor question. Like in normal steel reinforcement, we will go for the threading. Instead of go for the lapping, we will generally use the couplers and we will use the threading and all. Will it be possible for the GFRP bars also? That is my one question. And other questions which was very well in previous panelist, especially the thermal coefficient and the fire rating, etc. So that is all from my end. Thank you.
Thank you, Mantriji. I think Hoffman, you can reply to the question what he has asked.
Okay.
Yeah.
Sure. Just about coupler and threading, the technology is available for coupling. It doesn't rely on threading because cutting the fiber, we will largely reduce the performance of the bar. So we use another technology that Dextra developed using what we call a swedge coupler. So it's a sleeve that is extruded onto the bar. And actually the connection is two sleeves, a male sleeve and a female sleeve, and we can connect the two together. I would say the drawback of this is it's significantly more expensive than a lap splice. Okay. So in the end, for rebar application, we almost exclusively use lap splice. However, this connection becomes very important and actually necessary when we use the rebar to make an anchor, and typically an active anchor, any kind of anchor we need to tension. We can't splice it because we use the concrete to transfer the load through bonding. So we need coupler in that case to be able to apply the stress. So that's the only case we use the coupler. So technology is there, it's working, but for cost reason, as a rebar, we do lap splice.
Okay, thank you.
Thank you, Hoffman. Let me take to the third panelist, Engineer Navneet Gupta ji.
Yes. So good evening. In Hoffman, in his presentation, that's presented that it is a good alternative material to the conventional steel, and it has a number of advantages like high strength, low weight, and then less electrical conductivity, and it is fatigue resistance. But since like for the soft tie, we are using this material long back, say from 1998 in India. In soft tie, it is mainly because it is of a permanent nature. There, we are not worried about so many aspects of elasticity, even low transfer strength, and non-yielding or brittle failures. I think these issues need to be addressed as far as design is concerned. How we will take into account the ductility, and because its transversal strength is also less, that's why it is to be cut by the TBM easily and all. And it has a very high tensile strength that is only along the in one directions, but in the other directions strength is very less. So that also need to be addressed because it is an anisotropic material. So these are my concerns. The remaining points has already been covered by the other panelists. Thank you.
Thank you, Navneet. I think Hoffman, Engineer Hoffman, can you comment on that? I think he has gone to the little chemistry of the rebar and the compatibility with the concrete or this part.
Yes,
You want to comment?
yes. If you'll allow me, I understand. I see also in the question there's a lot of concern about shear, and I think it's mostly governed by the fact that we promoted so much GFRP almost exclusively for soft tie, as you explained again, Mr. Navneet Gupta. We said, oh, it's great, it can be cut easily by the TBM. Everyone has in mind, okay, high tensile but low shear. It is correct, but unfortunately, it's probably not fully capturing the aspect of the material. If you allow me, I'll try to show it in 3 slides. I'll show you something about shear because I think it could really answer the concern. So allow me just to put on screen something to explain the difference, I mean, and to answer that important concern.
Sure. Yeah, please go ahead, please.
Can you see again the presentation now? Yes.
Yes, we can see. Yes.
Okay, so I'll be very brief, but again, so when we talk about soft tie, when we talk about shear strength and cuttability, this is what we are concerned about. The bar easy to cut, the bar easy to shear, and why? Because it's the cutters of the TBM that will crush the bar. So what happens is the bar will be in direct contact with the steel blade, or typically what the TBM is doing is what I'm showing on the left side of the screen. What we call with the Dowell effect is the pure shear, that we can imagine. However, in most cases, and this is something where you see the title of my presentation is rock bolt for tunnels and cavern. We are supplying 500,000 rock bolt GFRP for permanent application in hard rock cavern. So I can tell you we had to go through a lot of those questions. What happened? In reality, when you are, it doesn't matter if you are in concrete and grout, you will have this kind of behavior. You will not shear the GFRP bar without any deformation. It will be able to crush the surrounding material, being concrete, being grout, being rock, before it completely fails. And that's why the GFRP rebar will have more shear strength than what we characterize normally with a simple shear test in the lab. I'll be again very brief. There's a lot of tests that have been done. We did some also on Dextra side, but to give you an idea, we did a comparative test. When we compare the pure shear strength of GFRP and steel side by side, GFRP only achieve 40% of a steel rebar. But when we do the same with surrounding material, with grout, but I repeat, with concrete would be the same. I go straight to the conclusion. Doesn't matter actually the concrete grade, 30 MPa, 40, 50 MPa. GFRP, thanks to the surrounding material, we're able to develop 75%. And why is that? is because of the when you allow some deformation, you don't have a pure shear deformation anymore. You have one component that is in tensile and one component in shear. And because tensile strength of GFRP bar is so high, actually having this split between the tensile and the frictional, you're able to get much more out of it. So there's even papers published about that. I would just wanted to conclude with that. At 90 degree, you see that GFRP rebar can develop around 350 MPa. That's according to this study. And that's really not that bad. It's 75% of what the steel bar would develop.
Thank you, Hoffman.
Okay,
I think it's a good reply. Thanks, Navneet ji, for asking really a good question. Actually, need to be addressed. With us, the IIB President Vinay Gupta ji is there. Vinay Gupta ji, a quick question from your side.
You want a question or you want any explanation as well?
Yeah, you can, sir. Over to you, sir.
Well, just to add to what Pierre said, you see, what happens that from the rebar, whether it's a glass fiber or it's a carbon fiber or whatever fiber, or it's a metallic reinforcement, we are neither looking for a shear strength, nor are we looking for a compressive strength, because most of it comes from the concrete. No doubt the design philosophy will be different, but we need some bit of shear strength and compressive strength for handling purpose. We are only looking for a tensile strength from glass fiber polymer reinforcement. Now you said question. The question I would like to ask Pierre is that why are we always talking about glass fiber polymer and not carbon fiber polymer, which has a higher tensile strength? Yes.
I think it's very easy answer for me is because of the size of the wallet.
It's a cost.
It's because it's a pure cost issue. I mean, to make things simple, all the rockets we send to the moon or to Mars and all the airplane we fly in the sky, they are made of carbon fiber because the strength to weight ratio matters the most. Okay, maybe to relate to our industry, all the repair job, I say all the repair, most of the repair job, when we have a damaged beam where we want to add a minimum weight of the material, typically under the beam, so where we have the maximum deformation, we use carbon fiber because carbon fiber would be 5 times lighter than steel and up to 4 times stronger. So you have a 20 times ratio. Here, it makes a lot of sense. But again, why we use GFRP in all this application where we install FRP, let's say from design point of view, not because we have an issue of repair in the first installation, is definitely for cost effectiveness reason.
I think Vinay Gupta ji, if I add, it is like 200 versus 1200 Indian rupees, the cost. So it is almost 6 times the cost. Okay, let me with us actually in the Vinay Gupta ji, if I let me go ahead with the second like in the panelists we have Dr. Surya Prakash Sahab. I think if somebody like his research and his PhD is in composites only, and he is a faculty in IIT Hyderabad. Professor, I will in fact you will answer all the questions and you will handle the questionnaire part.
Right.
So I will take a quick comment
Yeah,
or just a quick comment or question.
Yeah, sure. I think thank you. I think first of all, fantastic presentation, Engineer Hoffman. I think generally these questions extend for a long time, so I do seek your apology. I took liberty in answering few of them. Because I worked on it, I hope you don't mind. If you want to add more to it, you can please you can do it. I think it was a very this material has a very good potential for a number of applications, as you have correctly said, and you have demonstrated as well with number of projects there. It has been installed. From research point of view, of course, we have been doing a lot of work. the BIS standard for standardizing this material properties for these bars. So we have been trying hard to push this. It needs a way, and of course, seismic applications, performance requirement, fire resistance, all these are still, we need to address. Of course, there is a long way to go. In fact, what we are trying to do at IIT Hyderabad is, by adding some discrete fibers, what we are finding is we can reduce the bar requirement at serviceability, because the major thing is the elastic modulus of GFRP bars is, as you've said, 1/4. So your though the crack width limit is little higher, but then the deflections and others, so your reinforcement requirement goes high. So what we have found is by adding very small amount of these discrete fibers, in fact, that also we can offset it. So it becomes really cost advantageous when we add these fibers along with this, then you can get a completely durable material. And also these fibers basically gives you ductility. Even if it is failing in compression control mode, by adding fibers, it doesn't fail in an abrupt manner. So it gives a lot of ductility. We found really very good, interesting results. So I just thought I will add, I think, it was a very nice presentation.
Yeah, Professor, thank you very much. Let me ask one quick comment from another faculty, Professor Jyoti Busari ma'am. A quick comment from her. She is another IIB member. Yes, ma'am. Please go ahead.
Yeah. Actually, when we see this changing dynamics of our at least in some specific applications. But yes, all the properties that we are seeing, that is basically the tensile strength. Okay, it is enormous, and therefore creep durability as well as corrosion resistance, all these are very well addressed. But as even he has said in the presentation, but the real concern is the E value as well as your linear stress strain characteristic. So when it comes to the design, one has to be very, very careful when you're designing this with the GFRP bar. Otherwise, your failures will be really in a brittle manner. So because ductility, percentage elongation, all these things, it really does matter. So having said so, definitely CFRP as well as this GFRP, and even with the aramide fibers. Aramide fibers also, the research point of view, much research is going on using the AFRP bars. But as said, that it comes to the cost ratio, definitely GFRP, it is picking up a lot. So concluding this is that you are having the ASTM, EFMPA, these all to investigate these FRP properties, and also you are having right now only the ACI 440, which is giving you the guidelines for designing this particular GFRP bars. So we have to use it with the what you can say,
yes, ma'am,
and avoid the. That's it. Thank you.
Thank you very much, ma'am. Let me ask our senior engineer Suri sir for his quick comment.
Good evening. Nice presentation. Lot of information. It's a new material as far as our country is concerned for use it in reinforcing bars. I would like to request you if you could kindly share your presentation, because about 2 weeks back, IRC has constituted a special committee to form some guidelines for use of FRP. I am one of the members for that, and we have already had one meeting in this. And the committee would now like to go into all the details, whatever has been, questions, whether it is the, because designing of the structure with this is a challenging job, considering the ductility and all these. I don't want to get into it. And therefore, I think whatever information or experience and your this presentation you can share and send it to us, it will be very helpful to us when we are discussing, and I'm sure that it does give a positive information from your presentation, that on a positive note we can start working on having some kind of a guideline so we can use it here. Thank you.
Thank you very much, sir. I think Professor Mahesh Tandon is there. He was in attendee. Now he has been. Professor Mahesh Tandon, sir, your quick comment. Now we have. Yes, sir.
Can we give your presentation to IRC to Mr. Puri? But you have to make a choice.
Hoffman. Yeah, Engineer Hoffman.
Yeah.
Can you share your complete presentation?
Yeah,
to
absolutely.
IRC?
No, absolutely.
I have your presentation. If you permit, we can share it with Mr. S.K. Puri of IRC and also Professor Mahesh Tandon, who's coming next, who is the chairman of the IRC Code Committee for this materials. And
Absolutely. And maybe if you allow me just one comment, because there were the question about the code. In fact, in India, you're mostly using the European influence. I myself...
we'll take the question like Professor Surprakash will take a question in a rapid fire. Okay, I will let me cover all the panelists. Professor Tandon,
I wanted to check up in a normal reinforced concrete beam subjected to flexure. I'm not talking about shear, I'm just talking about flexure. If we replace the reinforcement bars with glass fiber reinforced polymer bars, what is the proportion of the ultimate strength of the bar that you can use, knowing that concrete means that maybe 75% of the weight is permanent? So it's a permanent stress, and creep will come into the picture. It has got an alkaline environment that is going to be a little detrimental. But finally, what is the value that we can use? As far as the strength is concerned, the strength of the bar, the tensile strength of the bar, what proportion can we use in flexure?
Okay. Again, if you look at ACI standard today, they will already offer you some answer to that. So they will have a creep factor, they will have a environmental factor that you would have to apply, a combination of them to get the right value. As we discussed in this presentation, the environmental factor would have to be at least 0.8. Today, ACI is saying 0.7, so it's the alkali environment. So today, ACI says 0.7. It will be updated to 0.75 or 0.8 probably this year. And creep will be limited to, again, 55. I think probably they will publish 50. So if you take the combination of those factors together, 0.8 times 0.5, it means at best, you can probably design with only 40% of the bar ultimate performance for long-term. That's, if I can give you a benchmark, in Australia, there's a Vic Road specification, and they allow 40% of the ultimate strength for the long-term design. So I think this is it's difficult to give you one answer because there's so many codes, but I would say there's a consortium in the industry, consensus, around this kind of value, around 40%.
So this 40% will be in the ultimate strength design, not in the service stage design. The stresses will be much lower, but in the ultimate strength design, of course, the load factors will come in because most of the factors, the concrete weight will have less safety factor. The live load will have more safety factor, partial safety factors, and all that. But finally, we are talking about the ultimate strength. 40% is what you can use, generally speaking. 40%.
Yes, sir.
Thank you.
Actually, Tandon Saab, see, the E value of this particular rebar is hardly 25% of the steel. So it will have a more elongation before failure. So most likely the concrete will fail first than the glass reinforcement. So even if you are going for a higher stress, even reaching to the higher stress, the concrete will fail because the E value of this particular bar is quite substantially low.
Right.
Yes. I think let me. I was holding intensely Dr. Harshvardhan Subbarao sir, not intensely, but I know you are one of the expert, world-renowned expert in the composite. Over to you, sir.
Yeah, thanks, Pierre. Very interesting. In fact, there is a crying need in India to address this material. Actually, it's from the Prime Minister's office and our Minister's office that there should be a drive to use this material and this innovative material in bridge and road construction. Now, the point arises like this. There are various factors which we need to address before we can use this. One is we talked about fire. Let's take one by one. We talked about fire. It's not the failure that we are talking about in fire. We're talking about the loss of bond, the bond which is so critical. So the bond degradation that may happen due to change in shape, the sensitivity to shape change, that is the issue here, and how that happens the mechanism by which that happens needs to be understood and addressed. That was one issue. The other, of course, is if you're limiting the design stress, the design ultimate limit condition to 40%, a lot of that material is actually going waste. Now, along with that waste in that material, there is also the fact that there's a shear lag through the diameter of the material. So the larger diameter bar has shear lag in the sense that the axial tensile stress will lag towards the center or gain towards the center, and the outer periphery will have a changed. So it is not uniform stress through the section. And the failure of the section will then depend upon where it is. It's at the core or at the periphery, because the stress distribution is not uniform through the thickness. This will also affect shear. Cross-directional shear will also be affected on account of this, against the direction of the longitudinal direction, I mean. Then the other issue that arises is the cover. You cannot limit and keep on. There is a limit if you're using it in a bridge deck. Even if you use steel reinforcement to replace some of the ductility requirement and the strength requirement, you can judiciously mix different types of fibers, discrete fibers, polypropylene, all these you can mix. You can even use polypropylene, for example, for fire resistance. To that extent, you can for the spalling. Yes, these are all possible. But what is not possible is to sacrifice robustness. You can never sacrifice robustness by making things thin, because that's what will happen if deflections will fail. As it is, we are in an anti-deflection situation compared to steel. Where 25% are E-value, so the deflection propensity is so much higher in this type of material if you use it in a bridge deck. Now, if you use it in a bridge deck and you start making things thin, because the diameter requirement, say if you need 24 diameter here, you need only 13 diameter. So I can drop the thickness of my bridge deck. Simultaneously, because it won't corrode, the propensity is to drop the cover. Then the slab becomes too thin. It becomes more prone to vibrational modes, vibrational fatigue. It becomes more prone to robustness and deflection. So these are issues. So there must be limits to what we can go, at which time this material stops making sense and steel actually has to come into play. That is the point. There's a limiting use to this material from these limiting factors. Okay. Then in which case the point arises, can we use a judicious mix of these materials? Can we use steel and this in tandem? And then the hybrid mode, how it might be addressed. You can't do all of it with steel fiber, you can't do all of it. You can do about 50, 70%, but you will still need steel somewhere along the way, depending upon the grade of concrete. We're not talking about M2 200, 200 MPa concrete. We're talking about a normal day use concretes, 50 grade and 60 grade and things like that, MPa. So this is one. Then the other question I have, which is worth looking at for the use of this material, is for the plastic confinement of a column. Now, in a typical steel bar, you have your 135-degree hook, the bent-in, invert bent-in hook, the 135-degree hook in, to ensure that they don't separate when the plasticity demand comes, say, at the base of a column. Now, if we use a bar like this with much lesser diameter and having sleek columns, thinner columns, making them more aesthetic, and we use this material with the lesser diameter and the lesser cover requirement, I then ask you, is it possible to use it for plastic confinement, which will be a great, great boon, if that is possible. Apart from other uses and the failure modes, the addressing of the failure modes, which you talked about, between crushing of concrete as well as the tensile rupture, those were basic modes, and the design ethos that will have to be more European than American, that Shirke raised as well.
Yeah,
so these are the points I want you to address or talk about.
Yeah, actually, these are questions which are raised in the question hour box also, some questions. So we will take, Engineer Hopkins, that same question we'll take but one of the like eminent panelists is there. Hegde sir, Engineer Hegde sir, can you give a quick comment so that we can go to the rapid hour questionnaires?
Yeah. Dr. Gopal Raj, thank you for giving me an opportunity to speak. I will not take much time, don't worry about it. And I should say this presentation has come in a very appropriate time, as Mr. Puri has very elaborately explained. In fact, I see 4 of the people who are in this, like the participants as well as in the among the panelists are there in that committee which Mr. Puri is talking about. And I think this presentation will be very helpful if it is passed on to Mr. Puri, and Puri in turn will pass it on to us. IRC is very keen, IRC in the sense ministry is very keen to use this material, because I think some of the people highest level in the ministry have gone abroad and seen this use of this material, and they have come back and they want to use this material. So a special committee has been formulated, and we are working on this particular FRP, that's a fiber reinforced polymer, and that is including carbon. It's not only the glass, as somebody has said, and we are coming out with a code. And also Dr. Surya Prakash, that from IIT Hyderabad, one Mr. Dr. Reddy is also a part of this committee. I'm sure that he will be taking an input from you, since you have done a lot of work on this. That's what I understand. So I think that's all from my end, Dr.
Yeah, thank you, thank you, sir.
I don't want to get into the.
Let me take a last comment from R.K. Goyalji, our own Indian Railway Chief Engineer. R.K. Goyalji, quick comment.
Yeah. Thank you, Dr. Gopal Rai, for giving me this opportunity. And congratulations to Mr. Hoffman for giving a wonderful presentation. It is definitely a knowledge upgradation for all of us. And I have got only one comment to make regarding the application part. A very good application he has suggested in the bridge decks. Actually, as a maintenance engineer, we are facing a problem of leakage through the bridge decks, which is creating the problem of falling of the concrete cover over the system running down under. And if we use this FRP bars, probably this problem of spalling, which usually occur after 25 years, 30 years, this can be addressed very effectively because there is no chance of any corrosion. So, and another application which I suggest, it can be in thermal reinforcement that we provide in PCC structures, because the whole purpose is to arrest the crack growth. And then this can be a very good application. So with this comment, I think it's a wonderful presentation.
Thank you.
Thank you very much for this.
I will take last comment from Engineer Swapnil Joshi, one of the civil engineer come project plan. Swapnil, can you give a quick comment?
Gopal, I won't be able to give a comment because I was not present because I had another meeting. So I just joined back. So sorry for that.
Yeah. Thank you. Honest enough for that. Thank you very much. Let me now hand over to Professor Surya Prakash. Then I will again back. Professor Surya Prakash, you can quickly go for the quiz.
Thank you. I think
Engineer Hoffman, now you have to answer, and Professor Surya Prakash will a quick fire round by question hours. We have almost 20 questions.
I think most of the questions need to be answered by Engineer Hoffman. I think that's
Please,
more
Professor,
appropriate. So one question from Mr. Ranjit Kumar is: rebending of FRP bars possible? Up to what extent it will affect the properties of the FRP bars if we start bending it?
I was about to answer that on the chat, but thanks for bringing it up. So sure. The short answer is today with the technology used is not limited by Dextra. It's all the bars available on the market. They are made of what we call thermoset resin. This resin can't be changed. The shape can't be changed at all. So the answer is absolutely no. It can't be rebent or bent. So if you order a straight bar, it will remain a straight bar. If you order a bend bar, it will remain a bend bar. However, there were a question about the performance. Actually, even if it's made in the factory, the bend portion will only have strengths that is about 50 to 60% of the straight bar. So basically, if you take a L shape, the two side, the straight portion will have the full performance, but the bend portion of it will only be 50 to 60%. So in the code, we use 50% only for the bend portion. That's because the fiber orientation has been changed, the matrix has been deformed. So it's part of the nature. It doesn't take as much load.
Thank you, Mr. Hoffman. Just quick adding on to it, is Dexter also thinking of developing thermoplastic based bars? So that would be basically help us to this bending issues. Any comments on that?
We are not thinking about it. We are doing it.
Okay.
It's happening. We work very closely with some major in the industry. We have done it. We were successful in having a bar that we can heat up locally. We have developed the machine to bend it. The main issue we have now is the strength retention in the bend section. It was much less in than what I mentioned now. So we have to work on improving that. It was also durability. At this stage, the loss of performance with the early stage test with thermoplastic, we couldn't get as much performance as we would get with thermoset resin. So we are working very, very actively on this. It's one of the big R&D projects that we are working on. But I think it will require some time, especially that none of the standard available today, international, local, none of them recognize those thermoplastics. So first, the technology needs to be developed and then needs to be accepted. So I think it will take some time before it reaches the market.
I'm moving on to the next question. What is the maximum length of bar that is possible and how the lapping is usually done? The question from Dr. Lakshmi Parameswaran.
So for shipping concern, today we deliver bars up to 11.8 across all 11.8 meters, across all diameters. In some specific cases, we were delivering bars even by 45 feet container in 13.5 meter, but that's exceptional. However, the beauty in working with small diameters, and again, that was mentioned, the shear lag. So the beauty with small diameter bar is they have the highest strength, as we've seen, but also they can come in coils. So up to diameter 13, we can deliver a coil, say 50 meter typically. And so therefore, if you have a project that requires long lengths, straight portion, you don't have to do a lap length of 750 mm every 12 meter. You can have a 50 meter long bar delivered to site and then cut to the exact dimension if needed. So that's possible.
Okay, thank you. So how about the performance of GFRP RC members under seismic loading? I think this is an expected question. Maybe you can just shed some light on it.
Yeah. I see a lot of people ask that. If I may answer that question, and maybe some of the, trying to even enlarge to some of the question, it is definitely not very well known, not very well documented. Some people are working on it, but I would say it's typically this kind of application that are not ready to market today. There's a lot of concern with seismic activity, and of course, I think ductility is one of the key feature to answer that. I think that's why I say to answer more large in more broader aspect. GFRP is today almost exclusively used for soft ties. There are some very challenging applications, like seismic application, that could be addressed. I think we need to accept to give it some time and go step by step. Bridge deck mentioned in the North America, they used it for 30 years. If you want to go for a bridge deck in India, you will find a lot of documentation, case study, and we can go and check how the design were made, and that would be possible. I'm not trying to refrain anyone to work on seismic activity project, but literally at this stage, it's on the plate of people doing R&D, publishing paper, research in universities. It is the kind of application we're not ready to do in the real world.
All right. Thank you. So next question is, could you please let us know if we have standard Excel sheets for design?
Professor, can you spell the name also, person who is asking question?
Yeah, from Mr. Samir Sawant. He's asking, are there any standard design sheets available from Dextra for designing for slabs, retaining wall columns, beams using the ACA provisions? Yeah, this is asking Hoffman. He's asking, are the ready-made available free in the open market? Are there any tools available?
So this is the short answer is no, because there are a lot of it's a bit complex, the way it's done, and some of the tools we use are not necessarily in Excel format, something we can share. So I would separate it.
I think we got connection.
Yeah.
Yeah. I think, Professor, questions are repetitive. Questions are there. I think a lot of questions are very repetitive, and I think one of the question which Dr. Harshvardhan Subbarao sir has asked regarding the compatibility and durability.
Yeah. So I would say to simplify the okay.
Hoffman, you have some network issue. I think he left again. He will join. There is Engineer Deepika. Engineer Deepika, you are also.
Yes,
can
sir.
Can you give your comment? Actually, this is one of the something material. Can you give your quick comment?
Hello.
Yes, Deepika. Please go ahead. I think you are not audible.
Sir, actually, I just missed out this. I'm just connecting with Mr. Pierre.
Okay.
Thank you.
Deepika, you can also give a comment. I think we can. I think more or less question we have answered, Professor Surprakash.
Yes.
There is only a few questions. Let him connect first. One question is there, which is always in my. I think Hoffman has connected, or he's there or not. Professor, there is a question actually. When I was studying my PhD from IIT Bombay, one of my senior was doing research in glass fiber rod. Okay, embedded in a beam. Okay, a RCC girder or beam, you can say, and he has checked. So the glass fiber used to get attracted towards the alkalinity.
Yes, sorry.
The glass fiber get attracted towards that time. I'm telling something about in 2002, 2003. Might be the material has been improved. That time when we have checked after aging test we have done, then the glass fiber glass rods used to give like some there is a attraction towards the alkalinity of the concrete. Whether we have improved on the, like I'm telling 18 years back, whether the material has been improved. Yes,
I think
Professor.
that's what Mr. Hoffman presented, right? I think there is a requirement that after 3,000 hours of, I think if I remember, exposure, the strength should not reduce by 20%. But most of the bars, at least, we have not done for the bars that are produced in India, but most of the bars which are produced like companies like Dextra, they easily meet that requirement. So there is not much degradation. So results have shown that they do perform very well. In fact, some samples were collected from bridges that were constructed 25 years ago, and they did the analysis. They saw that the degradations are very, very minor. So that means even after 25 years in service, that too in the harsh environment.
I think there's some echo. Yes, Professor, because I'm telling 20 years back, because when we have started in fiber wrapping and rehabilitation, earlier people used to put glass fiber. Now it is completely shifted to the carbon fiber. Okay, for the rehabilitation. Again, that time the cost and everything was there, but now the strengthening modes has been changed.
Yeah, I think cost is the issue. Cost is a major issue.
I think we have answered all the question. shall we give a mic to our engineer Swapnil Joshi so that he can? I think there is one more like quick comment I can say. There is some who is Bhargav Jog sir, Mr. Bhargav Jog sir.
Yes, good evening, sir.
Good evening. Can you give sir your quick comment, the last but not the least? Okay, can you give your first part? Yes, sir, please.
Yes, so we just wanted to, I'm from Dextra basically. So since, as we all mentioned, this is comparatively a new subject for all of us, the way we did for last time also the headed bar. Similarly, here also we have seen the application of more of a temporary application for this product line. So this is where we thought, since we will have all these eminent speakers and the panelists and all the expertise from this industry, we thought this would be a good, topic to discuss upon, where we will also learn from you. We can also share what technology, what work we are doing, and could be a good opportunity to connect all of us and jointly move together on this.
Yeah, I think your gesture was truly amazing. Like you are not only your technical sharing, also you are supporting the institution for the good cause. Really, thank you very much for all your support, and we wish Dextra keep doing the good thing for the nation and also for the engineering part. Thank you very much, Bhargavji.
Thank you.
And now let me give a formal to hand over to Swapnil Joshi ji, our Honorary Secretary of IIB. He is actually from Intento. He belongs to in the project planning and execution. And from last 10 years or 11 years, I know Swapnil Joshi, very calm, but whatever projects he takes on the planning stage and everything, that runs in a full speed, and sometimes it is concluded before the timeline or deadline. So I think the better person on the project management and all discussion, I think Swapnil is he's one of the honest guy. If he has not listened, then he will not ask question also. So over to you, Swapnil. Good.
Right. Thank you, Gopal. So I would like to formally present a vote of thanks. I would like to thank Engineer Hoffman for a very informative and interesting presentation. And on behalf of IIB, I would like to thank you for accepting our invitation on making a presentation. So thanks a lot. Thank you very much for your time. I would like to thank today's sponsor, Dextra, for their continuous support towards our initiative in dissemination of knowledge. Thank you very much for your support and continuous participation and joining hands with IIB. I would like to thank today's moderator, Dr. Gopal Rai, for his valuable comments and time. Thank you, Gopal. I would also like to thank for today's esteemed panelists, Engineer Navneet Gupta ji, Engineer Raj Shirke sir, Engineer Lakshmana Rao ji. Thank you very much for your valuable inputs and sparing time and giving your valuable comments on today's session. Thank you very much. I would like to thank today's participants without whom this event wouldn't have been a success. So thank you everyone for your patient hearing and continuous participation towards our lecture series conducted by IIB. Thank you. Also, big thank to all our senior members and AC members for their participation and continuous supports towards this lecture series being conducted. Thank you all. Then I would like to give a special thanks to our DG, Engineer DG Dute and President Vinay Gupta ji for their continuous supports towards taking the IIB to new heights. I would like to thank the team members, Deepika Singh from Intento, Ruhi Agarwal from DGC, Josefa for giving us a continuous support for IT, without whom it is not possible to have a seamless and smooth sessions or the lecture series what we are conducting. So with this, I hope I have not I have taken everybody's name, and if at all I have forgot somebody, please kindly excuse me. But thank you very much to everyone who has been participated towards this lecture series to make it a great success. Thank you very much, and I would like to officially declare that today's session is closed.
Thank you.
Thank you.
Thank you very much.
Thank you very much.
We are all to be safe, be at home, and do a good work. काम भी कीजिए लेकिन घर में रहिए.
Thank you everybody.
Thank you very much.
Thank you.
And take vaccination. Okay. Thank you.
Thank you.